Okay, question 6, we've got a distance time or velocity time graphs, and it says, which of these graphs represents an object moving with a constant velocity of 2 meters per second? Well, I can instantly rule out the velocity time graphs because this would mean that they're accelerating, so it can't be those. So now I'm left with these two choices, A and C, and I'm now looking for a constant velocity of 2 meters per second. So that just means in 1 second it's travelled 2 meters. So let's have a look. There's 1 second. Well, that's not travelled 2. There's 1 second. It's travelled 2. So it must be C. Next one, we've got a velocity time graph showing a 34-second part of its journey. Calculate the acceleration. So draw a little triangle, and we know A equals V minus U over T, but I've also taught you this is delta Y over delta X. So we've got to find out this change. So that's going from 14 to 26. That's a change of 12. And it already told us that this is a 34-second journey. So now we've got it. There's initial speed there, final speed there, and time there. So it's going to go from 14 to 26, which is a change of 12. So that's 12 over 34, or in full, 12 over 34 equals 0.35 meters per second squared. Done. Calculate the distance the train travels in 34 seconds. So if I just go back to this, so we can then see, right, let's have a quick look at how many marks it's worth. 3. So clearly we're not just going to do the triangle, we've got to do the bit that sits under it. So I've got section A, section B. This one's length times width over 2, and this one's just length times width. So it's then just work out each of those. Well, we know that this one was 12 and 34. We know that this one's 34 and 14, and we just got to times those together, and the top one divide by 2. So part A, 12 times 34 over 2 is 204. So we know in that section here it's gone 204. Now let's do part B. 14 times 34 is 476. There we go. We can see the two numbers that we used, and they've worked out that section. And what was it again? 476. And therefore we just add those two together, equals 680 meters. Okay, C. Figure 9 shows a rocket soon after takeoff. So we can see we've got the gases being pushed out that way, and then we've got a thrust upwards. So that's the gases. This is Newton's third law of action. Every action, there is an equal and opposite reaction. The force that the rocket engines produce remains constant for a few seconds after takeoff. Explain what happens to the acceleration during the first few seconds. So we've got Newton's third law there. If we look at Newton's second law, you'll know that as my fat auntie. We can see A equals F over m. So what we know is this rocket is going to accelerate and accelerate and accelerate, and that's because we've got the same force coming out from the gases, but this has got less mass. If it's got less mass, we're going to have a greater acceleration. All right. And it just says there the force remains constant. Okay, so we've got that. So crucially, if this bit's staying the same, that bit needs to be reducing. So here's our model answer. F equals ma, so A equals F over m. That's Newton's second law. Force is constant, gives us that in the question, so there's no mark for that, but the mass is decreasing as fuel is burned. So if mass is going down, this has got to be going up, acceleration's got to be going up. Therefore, acceleration increases. That's it, all done. And if you wanted to, you could use numbers in there, so I could go in there. So for example, acceleration equals 5 over 5 equals 1. Acceleration equals 4 stays the same, 5 over, and there's less mass, 2 equals 2.5. And I've just proven it with a tiny bit of maths showing what happens when the top number stays the same and the bottom number goes down because I've burnt some fuel.